The standard table of Laplace transform is shown, a part of it is shown in 7.1.1. So we have the Laplace transform of 1 in 1 as 1 over s, Laplace transform of t raised to the power an integer as n factorial over s raised to the power n plus 1, and Laplace transform of e raised to the power at is 1 over s minus 1. These are the simple functions for which I calculated in the previous video. Now we have to calculate for sine of kt, the sinusoidal functions, and the uh, the hyperbolic function sine hyperbolic kt and cos hyperbolic kt. So you can follow from the book. I will use the a slightly different way to prove to get those relationships. So the first example I'm going to attempt, and this is fifth example. I calculate the Laplace transform of cos hyperbolic of kt, and well, you can use with um, the definition from the definition of integral. I use it uh, with the exponential equivalent of cos hyperbolic kt. So it is e raised to the power kt plus e raised to the power minus kt and divided by 2. And earlier we developed the Laplace transform of these functions, e raised to the power at. So cos hyperbolic kt can be easily written as Laplace transform of kt. So it will be 1 over s minus k, and plus the Laplace transform of e raised to the power minus kt. So that will be 1 over s plus k. So very simple. So then it's a matter of calculating LCM. So s squared minus k squared. This will be s plus k plus s minus k. So k will get cancelled, and ultimately it will become s over s squared minus k squared. So this is the Laplace transform of cos hyperbolic kt. So instead of going through the route of integrals, I adopted the properties that I developed earlier. So is this one? Similarly, it is apparent that for the other parts function sine hyperbolic kt. So this is going to be with s over s squared minus k squared. It will be different than the cos hyperbolic. It will be with the constant k over s squared minus k squared. So I leave its verification for students. So cos hyperbolic kt, s over s squared minus k squared. I proved that one, and sine hyperbolic kt, that can be proved in with similar lines. So this is this one, and then let's calculate for sinusoidal functions. So example 6, Laplace transform of the function cos of omega t. So you can trace from the integral root 0 to infinity cos omega t e raised to the power minus st dt. So this integral can be evaluated and limits can be applied. But I'm going to use the definition I used in the context of hyperbolic Laplace transform of hyperbolic functions. So e raised to the power omega t is, it can be written as e raised to the power iota omega t plus e raised to the power minus iota omega t and divided by 2. And cos of omega t is basically the real part of this one. So real part of these complex exponentials. So I can use this definition for the calculation of Laplace transform. So I can write Laplace transform of cos omega t as the real part of Laplace transform of e raised to the power iota omega t plus e raised to the power minus iota omega t and divided by 2. So it will be a real part of Laplace transform of e raised to the power iota omega t. So I can write it as the Laplace transform of e raised to the power at. So it is 1 over s minus iota omega plus 1 over, for this part, the Laplace transform will be s plus iota omega, and this will be the real part of it. So 1 by 2, the real part of this one, this need to be evaluated. S squared minus iota omega squared, and then here it will be s plus iota omega. It's s minus iota omega. So, wow, luckily the imaginary part has naturally been eliminated. So it is 1 by 2 times 2s, and it is s squared plus omega squared, as iota squared is equal to minus 1. So then it becomes s over s squared plus omega squared. This is the Laplace transform of cos of omega t. This is analogous expression with a slight difference to the Laplace transform of cos hyperbolic of kt. So in that expression, there was the minus appearing. So likewise, sine of omega t Laplace can be calculated with the method I have just shown, or with the from the first definition. So that will turn out to be omega over s squared plus omega squared. So the set has been evaluated, the fundamental set of Laplace transforms, the very basic one. And now we can calculate the Laplace transform of a piecewise function, a discontinuous function. And that's the power of Laplace transform, that it helps us to solve the differential equations when the input is a piecewise continuous function, or there is a discontinuous function. We will include these Laplace transform while solving the differential equations. So in example 6, I have a function f of t defined as 0 from 0 to 3 in time domain, and beyond 3 it is 2. So that's a kind of a step function. Step functions are very useful in the signal analysis and the study of electrical systems to get the response against the step functions. So that is the picture of this function. That it appears as 0 from 0 to 3, and then from beyond 3, its value stays at constant value 2. So let's get its Laplace transform. So example, my numbering goes to 7. So example of a function, discontinuous function. So from it is 0 when time is greater than 0 and less than or equal less than 3. Okay. Is less than 3, and its value stays at 2 for t greater than or equal to 0. So it's a not greater than 0, greater than or equal to 3. So this is a discontinuous function. It is discontinuous at t equal to 3. We can calculate its Laplace transform using the first definition, the fundamental definition. So integral from 0 to infinity so it is from 0 to infinity e raised to the power minus st dt. So we divide this integral according to the function definition domain. So from 0 to 3, which is slightly less than 3, the function is 0. And plus from 3 to infinity, it is the value of function is 2 e raised to the power minus st dt. So the first integral will vanish because it does not exist there, and then the second one has to be evaluated with its proper limits. So e raised to the power minus st over minus s, evaluated from 3 to infinity. So it is 2 over s. Then limit t goes to infinity, e raised to the power minus st minus e raised to the power minus t will be replaced by 3 and then s. The first integral will vanish. The limit will vanish it to 0 and then e raised to the power minus 3s. So then it becomes 2 by s, and then e raised to the power minus 3s. So Laplace transform of the discontinuous function has been evaluated, and we got the result. So Laplace transform of many functions can be evaluated. And now our task is to find the Laplace transform of the derivatives. And that will complete our set for solving the differential equations. So in the next demonstration, I will calculate the Laplace transform of y prime, y double prime, and in general, if there is nth derivative. So with that set, our our requirement for solving a constant coefficient differential equation will be satisfied, and then we will move on to see the solution of constant coefficient differential equations against the inputs for which we have calculated the Laplace transforms. So let's stop at this point.